The Antikythera Mechanism. In 1901, off the rocky coast of the Greek island of Antikythera, sponge divers searching the sea floor encountered the remains of a Roman-era shipwreck resting more than 150 feet beneath the surface. At first, the discovery appeared routine: bronze statues, marble sculptures, coins, pottery. The cargo seemed consistent with countless other ancient shipwrecks recovered from the Mediterranean. Then, divers noticed a heavily corroded lump of bronze, unlike anything else aboard the vessel. When conservators carefully separated its fragments months later, they discovered rows of precisely cut bronze gears hidden inside. No one had ever seen anything like it. Ancient Greece had produced remarkable philosophers, mathematicians, and astronomers, but a mechanical device containing dozens of interlocking gears seemed impossible. The mechanism dated to roughly the 2nd century BCE. Mechanical clocks would not appear in Europe for more than 1,000 years. As researchers reconstructed the fragments using X-rays and modern imaging techniques, an astonishing picture began to emerge. The gears were not decorative. They formed an intricate analog computing system capable of predicting astronomical events with remarkable precision. By turning a single crank, the mechanism could calculate the positions of the sun, the moon, planetary cycles, eclipses, and even the schedule of the Olympic Games. Each gear ratio reflected advanced mathematical knowledge. Some gear teeth differed by only fractions of a millimeter. Modern engineers have described the craftsmanship as extraordinary for its time. Yet, the greatest mystery is not what the device could do. It is why nothing comparable appears again for centuries. No surviving workshop has been found. No instruction manual survives. No complete ancient description explains how it was constructed. Some historians believe it represented the pinnacle of Hellenistic engineering. Others argue it may simply be the only surviving example of a technology once far more widespread. If that is true, then countless similar devices may have been melted down, destroyed during wars, or lost beneath the sea long before archaeologists had the chance to recover them. The Antikythera mechanism does not rewrite history, but it reminds us that extraordinary knowledge can disappear just as easily as civilizations themselves. And if one mechanical computer survived by accident, how many others never did? Roman concrete. In 1748, laborers clearing volcanic ash near the ancient Roman city of Pompeii uncovered structures that had remained standing for nearly 17 centuries. Walls still stood. Harbor foundations remained intact. Massive breakwaters continued resisting Mediterranean waves despite centuries of relentless erosion. Modern engineers found something remarkable. Many of these structures were in better condition than modern concrete poured less than a century earlier. The difference lay hidden inside the material itself. Roman builders did not use Portland cement. Instead, they mixed volcanic ash, known as pozzolana, with lime and seawater. At first glance, the recipe seems surprisingly simple. Yet, microscopic analysis has revealed a far more sophisticated process. When seawater seeped into tiny cracks inside Roman concrete, chemical reactions gradually formed rare crystalline minerals, including aluminous tobermorite. Rather than weakening the structure, these crystals slowly repaired internal fractures. In effect, the concrete became stronger over time. Modern concrete usually begins deteriorating within decades. Steel reinforcement corrodes. Water enters microscopic cracks. Freeze-thaw cycles accelerate structural failure. Roman marine concrete often behaved differently. The ocean itself became part of the repair process. Researchers examining ancient Roman harbors discovered evidence of continuous mineral growth occurring for centuries after construction. The structures were not merely surviving, they were evolving. Historians believe Roman engineers arrived at this formula through generations of experimentation. Others suggest they understood volcanic chemistry far better than previously assumed. Entire ports, including sections of Ostia and Caesarea, continue to demonstrate the remarkable durability of this ancient material. Today, scientists around the world are attempting to reproduce the Roman formula. The goal is not historical curiosity alone. Concrete production accounts for a significant portion of global carbon emissions. If the Roman mixture can be replicated at industrial scale, it could dramatically increase the lifespan of modern infrastructure while reducing environmental impact. Ironically, one of humanity's oldest building materials, may help solve one of its newest engineering challenges. For nearly 2,000 years, the formula remained forgotten. Not because it was impossible, but because the civilization that perfected it disappeared. If knowledge capable of lasting millennia can vanish once, could it happen again? Damascus Steel. In the medieval markets of the Middle East, travelers told astonishing stories about swords unlike any others. Blades that sliced silk drifting through the air, weapons capable of cutting ordinary steel, edges that remained sharp after countless battles. European crusaders called them Damascus swords. Their distinctive rippling patterns looked almost like flowing water frozen into metal. But beauty alone did not make them legendary. Their reputation came from performance. Historical accounts describe blades that combined exceptional hardness with surprising flexibility. Many swords can achieve one quality, few can achieve both. Hard steel often becomes brittle. Flexible steel usually sacrifices sharpness. Damascus blades appeared to balance these competing properties with remarkable success. The secret lay in a material known as Wootz steel, originally produced in India before being refined by master smiths throughout the Middle East. Small ingots containing carefully controlled amounts of carbon and trace elements underwent repeated heating and forging. Minute changes in temperature dramatically affected the final structure. Too hot, and the internal pattern disappeared. Too cool, and the blade became fragile. The craftsmen possessed no microscopes, no metallurgy textbooks, no modern chemistry. Yet somehow they consistently manipulated the internal structure of steel with astonishing precision. Modern electron microscopy has revealed intricate networks of microscopic carbides woven throughout surviving Damascus blades. Some researchers have even identified carbon nanotube-like structures, although this interpretation remains debated within the scientific community. Regardless of the exact mechanism, the original manufacturing process eventually disappeared. By the 18th century, master smiths could no longer reproduce authentic Damascus steel. Trade routes changed. Sources of raw materials vanished. Generations of practical knowledge faded away. Today, modern metallurgists continue attempting to recreate the original process using surviving historical evidence. Many have produced visually similar blades. Few claim to have fully restored the lost techniques. The disappearance of Damascus steel illustrates a different kind of technological mystery. Sometimes knowledge is not destroyed in a single catastrophe. Sometimes it simply fades, one craftsman at a time. The Baghdad Battery. In 1936, while excavating the ancient settlement of Kujut Rabu near Baghdad, Iraqi archaeologists uncovered a small clay jar unlike any ordinary storage vessel. Standing just under 6 inches tall, it contained a rolled copper cylinder secured with asphalt. Inside the cylinder rested an iron rod. Individually, the components seemed unremarkable. Together, they formed something unexpectedly familiar. Nearly 2,000 years later, engineers noticed that the arrangement resembled the basic design of a galvanic cell, a simple battery capable of producing a small electric current when filled with an acidic liquid. The artifact dated to the Parthian or early Sasanian period, roughly between the 3rd century BCE and the 3rd century CE. If the jar had indeed generated electricity, it would predate Alessandro Volta's invention of the electric battery by almost 18 centuries. The idea captured imaginations around the world. Laboratory experiments demonstrated that replicas of the vessel could produce a modest electrical charge using substances such as vinegar, grape juice, or lemon juice. The voltage was small, usually less than 1 volt, not enough to power machines, but potentially sufficient for delicate applications. Some researchers proposed that ancient craftsmen may have used the device for electroplating, coating jewelry or ceremonial objects with thin layers of precious metals. Others suggested medical or ritual purposes. Yet no consensus emerged. No wires were discovered. No electrical workshop has been identified. No surviving ancient texts describe the intentional generation of electricity. Many historians argue that the object was simply a storage container for sacred scrolls or documents. Others believe the electrical explanation remains plausible but unproven. The debate continues because the artifact occupies an uncomfortable space between possibility and evidence. It is neither conclusively a battery nor conclusively something else. Perhaps the greatest lesson of the Baghdad Battery is not about electricity. It is about how easily modern assumptions shape our interpretation of ancient objects. Sometimes the mystery lies not inside the artifact, but inside the questions we choose to ask. The Iron Pillar of Delhi. For more than 16 centuries, an iron column has stood beneath the open sky in Delhi, India. It has endured scorching summers, relentless monsoon rains, seasonal humidity, centuries of pollution. Empires have risen around it and vanished, yet the pillar remains almost completely free from rust. Standing over 23 feet tall and weighing more than 6 tons, the iron pillar was erected during the Gupta period, one of ancient India's greatest scientific and cultural eras. Modern metallurgy teaches that exposed iron naturally corrodes. Given enough moisture and oxygen, oxidation becomes inevitable. But this monument seems to follow different rules. Researchers analyzing samples from the pillar discovered unusually high phosphorus content combined with extremely low sulfur and manganese levels. The ancient forging process created a thin protective layer known as mesawhite. Unlike ordinary rust, this microscopic film slows further corrosion by sealing the surface against environmental damage. The remarkable feature is not merely the chemistry. It is the craftsmanship required to produce such an effect more than 1,600 years ago. The pillar was forged without modern blast furnaces. No industrial steel mills existed. Instead, enormous blooms of wrought iron were repeatedly heated, hammered, and welded together by skilled metalworkers using techniques largely lost to history. Each stage demanded extraordinary precision. A mistake in temperature or composition could have ruined the entire structure. Even today, producing an object of comparable size through traditional forging would require exceptional expertise. Scientists no longer consider the pillar supernatural. Its corrosion resistance can be explained through metallurgy. Yet, explanation does not diminish admiration. Instead, it highlights the remarkable level of knowledge possessed by ancient Indian craftsmen. Their achievement reminds us that technological sophistication does not always require electricity or machines. Sometimes it appears in the quiet perfection of materials that continue performing exactly as intended, long after their creators are gone. Greek fire. In the year 674 AD, the Byzantine Empire faced one of the greatest threats in its history. An enormous Arab fleet sailed toward Constantinople. For decades, the expanding Umayyad Caliphate had conquered vast territories across the Middle East and North Africa. Now, the capital of the Eastern Roman Empire stood directly in its path. The defenders were badly outnumbered. On paper, the city's survival seemed unlikely. Then, according to Byzantine chroniclers, something extraordinary appeared upon the sea. Mounted on the bows of imperial warships were bronze tubes resembling the heads of mythical beasts. As enemy vessels closed the distance, Byzantine crews ignited a mysterious liquid and forced it through these siphons. A stream of blazing fire erupted across the water. The flames struck the wooden ships. Instead of dying upon contact with the sea, they spread. Sailors desperately threw buckets of water onto the inferno. The fire only seemed to burn more violently. Panic swept through the attacking fleet. Some crews abandoned their ships entirely, choosing to face the sea rather than the flames. The weapon became known as Greek fire. Its exact composition remains one of history's greatest military mysteries. Contemporary accounts describe a thick, sticky liquid capable of clinging to wood, cloth, and flesh. Some reports claimed it could even continue burning on the surface of water. The formula was considered one of Byzantium's greatest state secrets. According to historical records, only a handful of trusted engineers knew its complete recipe. Production occurred under strict imperial supervision. Knowledge was passed down through carefully guarded families rather than public workshops. Even when enemy forces captured Byzantine equipment, they never successfully reproduced the weapon. Historians have proposed many possible ingredients: petroleum, pine resin, quicklime, sulfur, naphtha. Perhaps some combination of all of them. Yet no surviving manuscript records the exact proportions or manufacturing process. Modern chemists have recreated mixtures with similar effects. None can be confirmed as the authentic formula. When Constantinople finally fell in 1453, the secret disappeared with the empire. One of the most feared weapons of the medieval world simply vanished. Not because it stopped working, because no one alive remembered how to make it. If an empire could lose a technology capable of changing naval warfare for centuries, how many other inventions disappeared alongside it? The south-pointing chariot. Long before the invention of the magnetic compass transformed global navigation, Chinese engineers described a remarkable vehicle that always indicated one direction: south. According to historical records dating back to the Three Kingdoms period, the south-pointing chariot carried a small wooden figure mounted on its roof. Wherever the vehicle traveled, the figure's arm continued pointing south, even as the chariot turned, even across winding roads. At first glance, it seems impossible. Many assume magnetism must have been involved. Surprisingly, it was not. Instead, the mechanism relied entirely on mechanical engineering. Inside the chariot, a sophisticated arrangement of gears functioned much like the differential gear found in modern automobiles. As the wheels rotated at different speeds during turns, the gear system automatically compensated for the vehicle's movement. The result was astonishing. The figure maintained its orientation without using magnets or celestial observations. Although surviving examples no longer exist, descriptions preserved in ancient Chinese texts allowed modern engineers to construct working replicas. The replicas demonstrated that the concept was entirely feasible. What makes the invention remarkable is not merely its function. It is the level of mechanical understanding required to create it. Differential gearing represents a sophisticated solution to a complex engineering problem. Most people associate such mechanisms with the Industrial Revolution, yet Chinese engineers understood the underlying principles more than 1,000 years earlier. Whether the original chariots were used regularly or served mainly ceremonial purposes remains debated. Some historians believe later accounts exaggerated their reliability. Others argue that repeated reconstruction across multiple dynasties suggests the technology genuinely existed. Either way, the south-pointing chariot illustrates a recurring theme throughout ancient history. Remarkable inventions often appear centuries before the world seems ready for them. Then, just as quietly, they disappear. The Lycurgus Cup. In 1845, collectors examining the possessions of a wealthy French family acquired an unusual Roman glass cup, unlike any other artifact known from antiquity. At first glance, it appeared ordinary. Under normal light, the vessel shimmered with a rich, jade-green color. But when light passed through the glass from behind, something extraordinary happened. The entire cup transformed. Green became deep crimson. The color shift was so dramatic that early observers believed it was some kind of illusion. The object eventually became known as the Lycurgus Cup, named after the mythological scene carved into its surface. For decades, no one understood how Roman craftsmen had created the effect. Ancient glassmaking was expected to be decorative, not technologically sophisticated. Yet, laboratory analysis revealed something astonishing. Embedded throughout the glass were microscopic particles of gold and silver. These particles measured only a few dozen nanometers across. Modern scientists call them nanoparticles. Depending on how light interacted with them, they scattered and absorbed different wavelengths, causing the glass to change color. Today, this phenomenon is explained by plasmonic physics. It forms part of the growing field of nanotechnology. The remarkable question is not whether the Romans understood quantum physics. They almost certainly did not. The mystery is how artisans, working with furnaces fueled by charcoal and guided only by observation, repeatedly produced glass containing particles so incredibly small. Many researchers believe the effect was discovered accidentally through generations of experimentation. Others argue that Roman glassmakers possessed practical knowledge of materials far more advanced than previously appreciated. Whether intentional or not, the result demonstrates extraordinary control over manufacturing techniques. The Lycurgus Cup remained unmatched for centuries. Only with the development of modern electron microscopes did scientists fully understand what had been hiding inside its walls all along. Sometimes, ancient technology is not impressive because it predicts the future. Sometimes it is impressive because it accomplishes extraordinary results without ever knowing the science behind them. The crystal lenses of antiquity. In 1850, while excavating the ruins of the Assyrian palace at Nimrud in modern-day Iraq, archaeologist Austin Henry Layard uncovered a carefully polished piece of rock crystal. It measured only a few centimeters across. To many observers, it seemed like little more than an ornament. But closer examination suggested another possibility. Its curved surface magnified objects viewed through it. The artifact became known as the Nimrud lens. Dating back nearly 3,000 years, it raised a fascinating question. Could ancient civilizations have understood basic optics long before the invention of modern lenses? The Nimrud lens is not alone. Archaeologists have recovered polished crystal and glass lenses from Greece, Egypt, Crete, and other parts of the ancient Mediterranean. Some are capable of enlarging fine details. Others concentrate sunlight into a single point. Their exact purpose remains debated. Some scholars argue they served purely decorative functions. Others suggest they were used by jewelers, scribes, or craftsmen requiring magnification for intricate work. A few researchers have proposed that such lenses may even have assisted astronomical observations. That idea remains controversial. No surviving ancient telescope has ever been discovered. No historical text clearly describes a magnifying instrument equivalent to later optical devices. Yet the physical lenses themselves undeniably exist. Experimental archaeologists have demonstrated that replicas can successfully enlarge inscriptions, assist engraving, and even ignite combustible material using focused sunlight. Whether these capabilities were intentional or simply fortunate byproducts of craftsmanship is still uncertain. What is clear is that ancient artisans possessed a surprisingly refined understanding of polishing crystal into precise shapes. Creating an effective lens demands patience. Minute imperfections distort the image. Surface irregularities scatter light. Producing a usable optical instrument by hand is far more difficult than it first appears. The existence of these lenses reminds us that technological progress is rarely linear. Ideas often emerge, disappear, then emerge again centuries later under entirely different civilizations. The Inca Stonework. High in the Andes Mountains, where earthquakes have shaped the landscape for millions of years, stand walls that should not have survived. The city of Cusco, once the capital of the Inca Empire, has endured countless earthquakes over the past 5 centuries. Spanish churches have collapsed, colonial buildings have cracked, modern concrete has fractured. Yet beneath many of these structures, the original Inca foundations remain almost untouched. Their secret is visible to anyone who looks closely. Each stone fits its neighbors with astonishing precision. No mortar holds them together, no visible gaps separate them. Some blocks possess 12, 16, or even 24 irregular sides, each carved to interlock perfectly with surrounding stones. Engineers have attempted to slide a knife blade between many of these joints. Often, it will not fit. The precision becomes even more remarkable considering the size of the blocks. Some weigh more than 100 tons. The quarries that supplied them lay miles away, separated by rivers, steep valleys, and rugged mountain terrain. The Inca possessed no iron tools, no wheeled transport for heavy construction, no draft animals capable of hauling such enormous weights. Yet, somehow, these stones were extracted, transported, shaped, and assembled with extraordinary accuracy. Spanish chroniclers who witnessed the structures shortly after the conquest expressed amazement. Some admitted they could not understand how the walls had been built. Modern archaeologists generally attribute the achievement to an enormous labor force, patient craftsmanship, and generations of accumulated engineering knowledge. Experimental archaeologists have demonstrated that stone can indeed be shaped using harder hammerstones, sand abrasion, and careful polishing. But one question continues to invite debate. How did builders achieve such consistency across thousands of individual blocks? The walls were not merely beautiful, they were practical. Their irregular joints allowed slight movement during earthquakes. Instead of collapsing under seismic stress, the stones shifted gently before settling back into place. It was an elegant solution to a problem that continues challenging engineers today. The Inca may not have possessed advanced machinery, but they clearly possessed an advanced understanding of structural stability. Sometimes the greatest technology is not the most complicated. Sometimes it is the one that survives longest. The Aeolipile. Nearly 2,000 years before steam locomotives transformed the modern world, an inventor living in Roman Egypt built a machine that hinted at a future no one would recognize. His name was Hero of Alexandria. Mathematician, engineer, inventor. Among the many remarkable devices described in his writings was an unusual sphere mounted between two hollow supports. When water inside the vessel was heated, steam escaped through two bent nozzles positioned on opposite sides. As the steam rushed outward, the sphere began spinning rapidly. Today, physics students recognize the principle immediately. It is the same reaction force that powers modern rocket engines. The invention became known as the Aeolipile. By itself, the device produced little useful work. It served primarily as a scientific demonstration, a curiosity, a mechanical marvel designed to illustrate the power of expanding steam. Yet its implications are extraordinary. The fundamental principle behind steam power had already been discovered during the 1st century AD, more than 1,600 years before the Industrial Revolution. Why, then, did ancient civilizations never build steam engines capable of powering factories, ships, or transportation? Historians point to several factors. Labor was inexpensive. Large populations of enslaved workers reduced the economic incentive for mechanization. Metallurgy had not yet advanced sufficiently to manufacture durable, high-pressure boilers. The supporting industries necessary for industrialization simply did not exist. In other words, the idea arrived before the world was ready. Hero's writings describe numerous other automated devices: temple doors that opened seemingly by themselves, coin-operated machines dispensing holy water, mechanical theaters performing miniature plays through hidden systems of ropes and gears. None transformed civilization. But together they reveal a society experimenting with automation long before the concept became practical. The Aeolipile reminds us that invention alone does not change history. Sometimes an idea must wait centuries for the rest of civilization to catch up. The Nazca water system. In the barren deserts of southern Peru, where some regions receive less than an inch of rain each year, an ancient civilization solved a problem that still challenges engineers today. The Nazca people flourished in one of the driest environments on Earth. Rivers flowed only seasonally. Groundwater lay hidden beneath layers of gravel and sand. For agriculture to survive, a reliable source of fresh water was essential, yet no massive reservoirs have ever been discovered. Instead, archaeologists uncovered something far more ingenious. Scattered across the desert are dozens of spiral openings descending deep into the earth. From above, they resemble giant stone whirlpools carved into the landscape. These structures are known as pukios. Each spiral leads into an underground network of carefully engineered tunnels. The tunnels intercepted natural aquifers flowing beneath the desert and carried water across remarkable distances before delivering it to farms and settlements. Unlike open canals, the underground passages protected the water from the scorching desert sun. Evaporation was dramatically reduced. Fresh water remained available throughout much of the year. Even more remarkable, many of these systems continue functioning today, more than 1,500 years after they were first constructed. Modern surveys have shown that the tunnels were carefully aligned with underground geology. Builders selected stable rock formations. Ventilation shafts maintained airflow. Maintenance access was incorporated directly into the design. The entire network operated without pumps, without electricity, without modern surveying equipment. Exactly how the Nazca located underground water remains uncertain. Some researchers believe they relied on careful observation of vegetation, soil moisture, and seasonal changes. Others suggest generations of accumulated local knowledge allowed them to map invisible aquifers with surprising accuracy. Whatever the explanation, the achievement demonstrates a profound understanding of environmental engineering. The Nazca civilization left behind no written language describing their methods. Their greatest engineering manual was the landscape itself, and centuries later, it still works. History often appears to move in a straight line, but archaeology tells a far more complicated story. Again and again, forgotten inventions like the Antikythera Mechanism, Roman concrete, Damascus steel, Greek fire, the Inca stonework, and the Nazca water system remind us that remarkable knowledge can disappear as easily as the civilizations that created it. None of these discoveries prove the existence of lost supercivilizations or impossible technologies. They reveal something even more extraordinary, that human ingenuity has always exceeded our expectations. People separated from us by thousands of years solved complex problems through observation, patience, experimentation, and generations of accumulated experience. Every excavation, every translated inscription, and every sunken ship adds another missing piece to a history that is still being rewritten. The past is not a finished story, it is an unfinished investigation. And somewhere beneath the next layer of Earth, another impossible technology may still be waiting to be found.